All right, so bond polarity. Bond polarity has to do a lot with, like I said, the different properties of molecular compounds. So if a bond is polar or nonpolar, it contributes a lot to what state of matter the compound is going to be in. If it's at room temp, it contributes to what their melting and boiling points are and all of that. And so before, we have to talk about bond polarity in order to talk about intermolecular forces. Now, if you take AP Chem is going to have an entire unit on intermolecular forces, and it's a big one. Because intermolecular forces is the reason we have different states of matter for covalent compounds. So what comes along with intermolecular forces is the properties of gases and the properties of solutions. And so in AP Chem, they're very, very important. So bond polarity. To determine bond polarity, you're going to use the difference in electronegativity. Okay? You're going to use the difference in electronegativity, so the change in electronegativity. So if you have a fairly large difference in electronegativity, then you're going to have a polar bond. Well, if you have a very, very large difference, it's going to be ionic. If you have a semi-large difference, it's going to be polar bond. Not a large difference, it's going to be nonpolar. So if your change in electronegativity or your difference in electronegativity is less than 0.3, so that means that if your electronegativity values are similar or the same, you're going to have a nonpolar covalent bond. Okay? If your change in electronegativity is from 0.3 up to 1.7, so you have somewhat of a difference, but not a very, very big difference. This is going to be considered a polar covalent bond. Okay? And then if your difference in electronegativity is 1.7 or greater, that's going to be considered an ionic bond. Okay? So here's an example of those differences in electronegativities. So again, if you have a difference 0.0, if your difference is 0.0, that means you have the same electronegativity value, which means it's probably the same compound. So you think of those diatomic molecules, those are going to have the same electronegativity value. To 0.3, so if your difference is just a 0.3 of a difference, that's not a very big difference. That's going to be considered non-polar covalent. That means you're sharing the electrons almost equally. Okay, think of a tug of war. If you cloned yourself or you're playing tug of war with someone who has very similar body structure, you're going to be sharing that rope pretty evenly. Then we have our difference in 0.3 to 1.7. This is a polar covalent compound. So you're still sharing that rope. You're still playing tug of war. But one element, the element that has the higher electronegativity value, is going to be pulling those electrons closer to itself. And what happens, we're going to discuss this, but what happens is when it pulls those electrons closer to itself, it gives these partial charges. Now, they're not full charges. It's not a full transference of electrons, but it gives these partial charges within the molecule that causes certain properties to happen. So one element may have a larger electronegativity value. Think of that as kind of the element being stronger. So when they're playing tug of war with these electrons, the one with the higher electronegativity value is going to be pulling those electrons closer to itself, and it's going to give itself a partial negative. Whereas the one that's weaker is going to be the electrons are going to be pulled away from them. That's going to give them a partial positive, because think of what electrons are. They're negatively charged, right? Now again, it's not a complete transfer, so it's not a complete charge, but it's just a partial. Okay, and then if your difference is 1.7 and 4, that's going to be a complete ionic bond. So there's a complete transfer there. One compound completely pulled the electrons from the other. Now remember, electronegativity values on the back of your notes, you'll have those. So these are just examples of what those values may look like. So if you have a bond between hydrogen and fluorine, that's going to be a highly polar bond. But if you look, the difference between hydrogen and boron is only 0.1, so that means that that bond is going to be a nonpolar. Okay? And then the difference between lithium and fluorine is going to be a 3, and so that's going to be an ionic bond, a complete transfer. Okay? Now, for polar bonds, we can show how the bond is behaving. Okay? What we do is we use this thing, it's called the direction of pull. And I've already kind of illustrated it. So the direction of pull, you're going to place an arrow above the bond pointing to the more electronegative element. So an example of that would be like this arrow. So we have hydrogen and chlorine. Even without those electronegativity values on the back of your notes, you can just look and follow the trend of electronegativity on the periodic table. As you go across a period, it increases, right? So chlorine is going to be more electronegative than hydrogen. Therefore, chlorine is going to be pulling those electrons towards itself. And so that arrow shows where the pull is going. So the electrons are being pulled towards chlorine. And then on the hydrogen end, we kind of put this plus, because that's probably what's going to end up happening is since chlorine is pulling its electrons, it's going to end up having a partial negative charge, and hydrogen is going to have a partial positive. So those are called partial charges. Okay, it's not a full charge. It's just a partial charge. Okay. So it says show the direction of pull and identify the partial charges of poles in an HO bond and a CCl bond. Okay, so we got an HO bond. Now, if we're using our electronegativity values that are on the back of our notes, we can assign those. Hydrogen's electronegativity value is 2.1. Oxygen's is 3.5. Okay? So, if we show that bond, who's going to be pulling the electrons closer towards itself? Oxygen. Oxygen has a higher electronegativity value. Therefore, it's going to be pulling those electrons closer to itself. So will oxygen have a partial positive or partial negative? Partial negative. Oxygen's pulling those electrons, so it's going to have a partial negative, and hydrogen's going to have a partial positive. Okay? Now, if you took the difference in an electronegativity here, what would that difference be? 3.5 minus 2.1 is 1.4, which means that this is a polar bond. Okay? That's why we showed those partial positives and negatives. Then we have our CCl bond. Okay? If you look, carbon's electronegativity value is 2.5 and chlorine's is 3.0. Okay? What is the electronegativity value difference? 0.5, right? So is that polar or nonpolar? This is still polar, right? It has to be below 3.3 or below. Okay? And so, this is still a polar bond. Who's going to be pulling the electrons closer to itself? Chlorine. Chlorine's got a higher value. Therefore, chlorine's going to be pulling those electrons. So chlorine will have a partial negative. Carbon will have a partial positive. Okay? Now, this is just talking about bond polarity. We're just looking at one bond between two atoms. Okay? Now we're going to talk about the polarity of an overall molecule, because you can have polar bonds within a molecule, but the overall molecule can be nonpolar because they tend to cancel each other out. Okay? So to determine molecule polarity, we have to look at the overall molecule. Okay? So to determine the polarity of a molecule, you have to look at the overall molecule, because there could be, like I said, there could be polar bonds within the molecule, but the overall molecule could be nonpolar. Okay? Because they could cancel each other out. If there is no overall pull in one direction, meaning the molecule is symmetrical. Okay? Then we have a non-polar covalent molecule. Okay? If there is no, if the molecule is symmetrical, if they're pulling in different directions, but they're all pulling the same strength, I guess is a good way to say it, then it's going to be considered nonpolar. Now, if there's a pull in direction of the molecule, or if there are unshared electrons, on the central atom. Okay, so either if it's surrounded by different elements, so if a carbon is surrounded by different elements, those different elements are going to have different pulls, correct? Or if your central atom has an unshared pair of electrons, those unshared pair of electrons is actually a pure negative charge. Both of those are going to cause a polar covalent molecule. Okay? So if you have different elements around the central, or if you have an unshared pair on the central, you're going to have a polar covalent molecule. So it says, note, in AP Chem, there are some expanded molecules that have unshared electron pairs on the central atom, but they're still in even distribution, according to the Vesper shape, creating a symmetrical nonpolar molecule. But for this year, we can use this simplification. So when you get into AP Chem, there's some Vesper shapes that may have like an unshared pair on top and an unshared pair on bottom. Okay? That cancels each other out, which causes a nonpolar molecule. But for this class, if there's an unshared pair on the central, it's going to be polar. Because the Vesper shapes we looked at, all of them that have unshared pair on the central is going to be polar. Y'all follow? We didn't look at the shapes that they're talking about. So to simplify, does the molecule look the same all the way around? If it does, then there is a nonpolar molecule. If it does not look the same all the way around, it's a polar molecule. Okay? So, if there are only two atoms on the molecule, then the bond polarity is the same as the molecular polarity. Okay? So if it says, note, if there are only two atoms, so like HCl is only two atoms, right? All you're looking at is the bond polarity here. Okay, because, I mean, there's not a central, is there? No. You just look, two different elements, polar, same element, nonpolar. Okay? Now, water is polar because, remember that oxygen has two unshared pairs on it, right? Water is polar because oxygen has those two unshared pairs, and there's a difference in electronegativity between oxygen and hydrogen. It's actually very polar. Water's very polar, and we'll talk about, when we talk about intermolecular forces, we'll talk about what that means by being very polar. But yeah, so for each of the following, determine if the molecule is polar or nonpolar. So remember, if it's polar, it either is going to have different elements surrounding it and or an unshared pair in the middle. Okay, so looking at this first one, PF3, is this polar or nonpolar? Polar. Why? Why is this polar? Unshared pair on my central, right? I have the same element surrounding it, but that unshared pair on the central is going to cause it to be polar. Okay? Now, CH4, polar or nonpolar? Nonpolar. Okay, CH4, this is methane, is nonpolar. We have the same element surrounding the carbon, and the carbon has no unshared pairs. Okay, so there's the same pull coming from all directions. Now, CH3Br, polar or nonpolar? Polar. Polar because we have three hydrogens, but we also have that bromine. That bromine is going to be pulling the electrons in that direction. Okay, so that's going to be polar. What about BCl3? We're going to say nonpolar. Okay, nonpolar for now. Okay, same element surrounding the central. Okay, next one, SO3. Nonpolar. Okay, so even though there's a double bond, it's still going to be considered nonpolar. Okay, now BeCl2, what is that? nonpolar. Same element. Okay? It's literally like a line. Same element, pulling in the same amount of pull in both directions. HCl. Polar. Okay, HCl is going to be polar. Two different elements. That's going to cause it to be polar. Okay? Now, molecular polarity determines properties. So like I said, polarity determines a lot of different kinds of properties. It determines melting and boiling point. It determines state of matter at room temp, and it also determines solubility. Okay, solubility is the ability to dissolve. Is it going to dissolve or not? Okay, so the solubility rule for covalent compounds dissolving in other covalent compounds is like dissolves like. Okay, like dissolves like. So, polar molecules dissolve other polar molecules, and nonpolar molecules dissolve other non-polar molecules. So it says oil and water do not mix. Why? Because water is a polar molecule, but oil is nonpolar. Okay? Water is a polar molecule, oil is a nonpolar molecule, so they are not going to dissolve into each other. That's why they separate out. Okay? So, excuse me, they have to be polar dissolves polar, or nonpolar dissolves nonpolar. Okay? Now I'm going to skip these two examples so we can move on to intermolecular forces. Okay? We can come back to that if we have time. Alright? Now, polarity is going to determine intermolecular force. Okay, there's actually 4 types that we're going to look at. But polarity will determine that, also type of bond. But so as a reminder, intermolecular forces are the attractions between the ends of molecules. Okay? Intermolecular forces are attractions between the ends of molecules. So the bonds on the inside of the molecules determine the forces on the outside. So the types of bonds that we have inside the molecule is actually going to determine the type of intermolecular force between the molecules. Do y'all follow? So the type of bond within the molecule determines the intermolecular force between two different molecules. So, however, bonds are much stronger than forces. Okay, don't get those two confused. Bonds, like the bond between oxygen and hydrogen, is much stronger than the intermolecular force between water molecules. Okay? It takes a chemical change to break a bond, but only a physical change to break a force. Okay? So remember, at the beginning of the unit, I said a bond is like a weld. If you weld two metals together, that's very, very strong, right? Now, a bond is like a weld, so the bond between oxygen and hydrogen, like a weld, it takes a lot of energy to break that, a chemical reaction to break. But the force between two water molecules, that say the force that holds your water in your water bottle together, that force is like a magnet. It's a lot easier to break. It only takes a physical change, so just like an increase in temp, okay? When the intermolecular forces break, it's still water. Okay, steam is still H2O, right? When the bonds break, it's no longer water. Okay, so those are the differences. So let's look at the type of intermolecular forces, these forces that hold molecules together. Now the first one actually technically is not an intermolecular force, it's just a, it's technically a bond, but it's called an ion-ion force. Okay, this is what holds ionic bonds together. Okay. This is present in ionic compounds, okay? It's the attractions between cations and anions. So technically an ion-ion force is the bond itself. That's why ionic, it's not called intermolecular, or it's not called interforces, it's called intermolecular forces, because those forces only really occur between molecules, because the force that holds ionic compounds together is the bond itself. Do y'all follow? That's why ionic bonds have such a high melting and boiling point, because in order to change the state of an ionic bond, you have to break a bond, not a force. Okay? So these are very strong. My pen's running out. These are very strong. It takes a lot of energy to break them. Let me grab a pencil. They have very high melting and boiling points. So like when you are, I don't even have lead in it. I don't have it. Sorry, all my pencils are going to be. Okay. So these have very high melting and boiling points. So that's why, like when you're cooking and you salt, say like you're cooking a steak or something and you put salt on it, that salt that's sitting in the pan does not melt, right? Okay, that's because the melting point for salt, for sodium chloride, is very, very high, because like I said, in order to change solid salt into liquid salt, you have to break bonds, and that's going to take a lot of energy. Okay, whereas if you put sugar in a pan, that's going to melt, right? Because what you're doing is you're not breaking bonds of sugar, you're breaking the forces between the sugar molecules. Okay, so that's how you make caramel. So this is the reason why ionic compounds are typically solid at room conditions. Okay, so ionic compounds are solid at room state, or at room temp, because they have very high melting and boiling points. Okay, so that's our first type. Now our second type, I hate that they named it this. They named it hydrogen bonding, but it's not a bond. Okay? Hydrogen bonding is actually a force. I know. Why would they name that? Because they love to confuse you guys. Okay? So the next one is hydrogen bonding. Okay, this is actually an intermolecular force. This is not a bond. It occurs because of a bond with hydrogen. But the actual force itself is not a bond. Okay? So hydrogen bonding, this is present in polar covalent molecules with an HF, an HO, or an HN bond. Hydrogen has to be directly bonded to fluorine, oxygen, or nitrogen in order to have a hydrogen bond. Okay? So if you do not have a section of your molecule that hydrogen is directly bonded to oxygen, or hydrogen is directly bonded to nitrogen or fluorine, that's not a hydrogen bond, because it's a very special case. So a good way to remember it is hydrogen with fun. Okay? Fluorine, oxygen, nitrogen. Now, partially positive and partially negative ends of the molecules attract. Okay? Now, this partial positive and partial negative in a hydrogen bond, they're actually very extreme. Okay? This is why, especially the partial positive. What happens, hydrogen, oxygen, or nitrogen, oxygen, and fluorine are some of the three most electronegative elements on the periodic table. They are. Okay? They're the three most electronegative elements. So what they're doing is they're pulling that electron away from hydrogen. Now, hydrogen only has one electron, right? What happens is they're pulling that electron away from hydrogen, and that one electron is being pulled closer to oxygen. What happens is the positive nucleus of hydrogen is actually being exposed. Okay? So hydrogen has one proton, one electron, right? Well, when that electron gets pulled away from itself, from hydrogen to oxygen or fluorine or nitrogen, the other side of that hydrogen atom is going to be exposed, or the other side of that hydrogen atom is an exposed proton, which gives you really, really, really strong partial charge on that side. Okay? So, the presence of hydrogen with fun strengthens that attraction. This is a strong force. Okay, I know in biology you probably learned hydrogen bonds are weak. Ugh. They're weak because they're not even bonds. Okay, that's why they're weak. But when we're talking in terms of intermolecular forces, technically the ion-ion force isn't even a force, right? It's not even a force between molecules. So if you're talking about forces between molecules, hydrogen bonding is the strongest, okay? Those are going to have high melting and boiling points. Water, for a molecular compound, has a high melting point, okay? Now, that's in general. You'll learn, again, in AP Chem, there are exceptions to that. Like, there are some dispersion forces that have higher melting boiling points, but we don't have to go into that, okay? Now, the next one, so that's hydrogen bonding. Next one is dipole force. What does di mean? Two, so two poles. Dipole force is present in all other polar covalent molecules. So if you have a polar covalent molecule and it is not hydrogen bonded to fun, then it is a dipole force. Okay? Remember, polar covalent molecules have permanent dipoles. We call them permanent because one atom is pulling the electrons away from another permanently because they're different in electronegativity. Okay, so partially positive and partially negative ends of molecules attract. Okay, these are permanent dipoles, permanently being pulled. Now, you may say, well, there's a hydrogen there. Isn't that a hydrogen bond? No. Why not? Why is this not a hydrogen bond? Because it's not bonded to fun, right? It has to be fluorine, oxygen, or nitrogen. This is bonded to chlorine, so this is just regular old dipole. Okay? Now, these are a medium force. They have medium melting and boiling points. So you'll see some that have maybe a gas at room temp, some that may be a liquid at room temp. It just depends on the molecule and all of that. Okay? Now, the next, or the last intermolecular force, these are called London dispersion forces. Okay? London dispersion forces. Okay, the only intermolecular force that's present in non-polar covalent molecules. So anything that is a non-polar covalent molecule is going to have a London dispersion force. Okay? All covalent compounds are capable of London dispersion forces, but the other types of intermolecular forces dominate, since all other types of intermolecular forces are stronger. And you'll see why. Everyone can have a London dispersion force. All molecules can, because it just involves the dispersion of electrons. So the electron cloud gets temporarily distorted, creating a temporary poles. Creating temporary poles. So what happens? Electrons, are they just sitting in the atom? Are they just chilling? No, electrons are moving, right? Electrons are constantly moving around that molecule. And what happens in that constant movement, what's going to happen at one point in time, you're going to have more electrons on one side of the molecule than the other, because they're constantly moving around. So you may have a point where there's going to be more electrons on one side than the other. What happens is if the electron density is higher on one side, that's going to give that one side with the higher electron density a partial negative charge, which gives the other side a partial positive. Well, this causes a domino effect. If I have a partial positive on one side, that's going to attract the electrons from the molecule next to it towards that side, right? And so it's going to be this domino effect, and that causes the molecules to stick together. Now, this is temporary because the electrons, again, they're moving, right? So they have those temporary dipoles, and they're going to move out of them. They're move back into them, they're move back out of them. So it's kind of this back and forth of these temporary poles. Now, this is a weak force. Okay, they have low melting and boiling points. So this is the reason why many small nonpolar molecules typically are gases at room conditions, such as carbon dioxide. Carbon dioxide is a nonpolar molecule. It is a gas at room temp. Okay, because the forces that hold carbon dioxide molecules together are very small. Okay. Now it says AB extension, as the size of molecules increase, therefore increasing the total number of electrons, the chance of temporary distortion is greater, meaning the larger molecules will have slightly stronger forces than their smaller counterparts when having the same intermolecular force type. There are some nonpolar covalent compounds that are solids at room temp. An example would be butter. Butter is a solid at room temp, right? That's because butter has these long hydrocarbon chains. And if you have these long hydrocarbon chains, the dispersion force is all throughout that chain, and they're able to stick together better or stronger. You have a ton of electrons, and they're flat too. If you're round, you're going to have a harder time. It's going to be easier to break, right? But if you're flat, these long hydrocarbon chains with all these electrons is going to stick together better. So that's why some nonpolar covalent compound dispersion forces actually may have higher melting points than dipole-dipole or hydrogen. Okay? But in general, we're going to talk general. We're talking about small molecules. We didn't talk about hydrocarbon chains, right? We're just talking about these small molecules with one central atom. In general, they're going to have low melting points. Okay? So let's look at the back. Let's look at some examples. Okay? Hydrogen sulfide. It says, for each of the following, determine the dominant type of intermolecular force between the molecules. Then put them in order of increasing melting and boiling points. Okay? So, hydrogen sulfide, we have to draw our structure. Okay? Hydrogen's got, this is going to be 2 electrons, sulfur's going to have 6, so that's 8. So 2, 4, 6, 8. Okay? So that's our structure. Now, is this going to be polar or nonpolar? Is this compound going to be polar or nonpolar? Polar. Why is it polar? It has unshared pair, right? It's got 2 unshared pair on the central. This is a polar compound. Let me ask you this. Let me draw it. What shape will this be in? What shape? What's our ABE formula? A, B2, E2. What is A, B2, E2? Bent. Okay. This is a bent compound. Okay. Now, so this is a polar compound. So we're asking for the dominant type of intermolecular force. Now, I see a hydrogen here, but is it bonded to Fon? No. So what type of intermolecular force? Polar covalent. What type? Dipole-dipole. This is a dipole-dipole intermolecular force. Okay? We'll do the ranking at the end. Now, next is methane. I'm just going to draw it for y'all. This is methane. Okay? Polar or nonpolar? Nonpolar. This is a nonpolar covalent compound. What's the shape? ABE formula A, B4. What is that? Tetrahedral. Okay, tetrahedral. So what type of intermolecular force here? If it's nonpolar, it's what? London dispersion. Okay. Notice all of the stuff is coming together, right? You have to be able to draw the structure to tell if it's not polar or nonpolar, and to tell what shape it is. And then you use your polarity to tell what type of intermolecular force. Okay, they're building, right? You got to be able to draw the structure to tell the shape, the intermolecular, the polar or nonpolar, which tells us the intermolecular force. Okay. Next one, lithium bromide. Well, lithium bromide is actually a what type of compound? What type of compound is lithium bromide? Ionic. This is an ionic compound, right? So, what kind of dominant IMF is going to be? Ion, ion. Okay? Ion, ion. Last one, ammonia, NH3. Okay, so this is ammonia. Is this polar or non-polar? Polar. What's the shape here? What's our shape? Trigonal what? Pyramidal. Okay, trigonal pyramidal. A, B3, E. Okay. Now, what type of intermolecular force? Hydrogen. This is a hydrogen bond. Why? Why is this a hydrogen bond? Because hydrogen is directly bonded to FON, right? It's directly bonded to nitrogen. That is a hydrogen bond. Okay, now rank of melting and boiling points. So 1 is going to be your highest melting, 4 is going to be your lowest. So what is our highest here? Ion, ion, right? Ion, ion is going to be our highest melting boiling point. What's our lowest? London dispersion. Okay. Now between dipole, dipole, and hydrogen, which one's going to have a higher one? Hydrogen. Okay, and then dipole, dipole. Okay, now this is something that, again, you've got to study. You've got to be able to identify, because we're literally going to give you something like this. You're going to have all of these sections. You're going to have draw the shape, tell me the shape, or draw the structure, tell me what the shape is going to be, tell me if it's polar or non-polar, and tell me what type of intermolecular force. Okay, so this is builds fast. So it's very important that you understand this. Okay.